Thank you very much, Jack, for that introduction. Thank you for the invitation to be here. It's a great pleasure to come to Arkansas this time of year and have such beautiful weather. I'm very interested in this whole process we're going to go through today. And in order to introduce this, I want to do essentially three things. So I want to talk a little bit more about convergence and start with NSF's position on convergence and how it arose. Talk about GIScience and GIS as something that is all about convergence and integration. And then I want to give some examples. And then I want to end with some discussion of a particular direction of opportunity, which I think should resonate with at least some of us, but is of course only one of the possible directions, one of the possible opportunities as we go forward. So here's what perhaps is the most seminal work that stimulated this entire effort at NSF. This is co-edited by Bill Bainbridge, among others, who has been a long-term thought leader at NSF. And it discusses the concept of convergence. It talks about the convergence-divergence cycle, which is an interesting proposition. The idea that science periodically moves from a phase of divergence in which the disciplines go off and do their own thing to convergence in which they realize how important it is to come together. I'm not sure that it's clear where we are in that cycle, or even if there is a general cycle, or whether it's something that influences different communities at different times. But that notion of cycling between convergence and divergence, I think, is important. Convergence defined as integrating knowledge, methods, and expertise from different disciplines and forming novel frameworks to catalyze scientific discovery and innovation. And many of us in GIS will immediately recognize some of those words as defining what we do. And just to be a little bit more explicit, here's GIScience and convergence, the notion that GIS is an integrating technology, something we teach right from day one in courses in GIS. The notion you're integrating layers of data to be able to say something about interactions between those layers. Clearly there's a strong dependence on the map in the sense of layer, but at the same time integration across layers is a key idea in GIS. So that's where, of course, many of us came from, starting back in the 1960s. And this idea of integration is, as I say, has been a long-standing central idea in GIS. If we move now to GIScience, this is a diagram that we worked up in 1997, I think, trying to rationalize GIScience and show how it addressed the interests of different groups. So we thought of a triangle, and we thought of the vertices of the triangle representing the computer or computer technology, society, and the individual. And we argued that any issue in GIScience could somehow be positioned in this triangle. So issues of human-computer interaction are on the northwest edge of that triangle, if you like. Issues of interactions, of the role of computers in society are on the bottom edge. And then many other issues, such as privacy, can be positioned within this triangle. So we thought it was a useful framework for thinking about geographic information science. But further to that, in 1999, Santa Barbara was awarded the Center for Spatially Integrated Social Science. This was one of a number of awards made by NSF at that time, awards in social science infrastructure. So the notion that GIScience could be the basis for an infrastructure underpinning the social sciences and integrating them was a very central idea. If you're interested further, there's a book, Oxford University Press, came out in 2004, edited by me and Don Janelle, which was a series of contributions on this notion of spatially integrated social science. And there's an article in International Regional Science Review in 2000, which laid out what we were trying to do in this center. And I believe there's also another book edited by Bob Stimson, came out in Australia. And there's also a PhD program at the University of Toledo on spatially integrated social science. Our objectives in this center were first to argue that spatial concepts and tools were integrating themes that cut across the traditional boundaries of the social sciences. Right? So spatial analysis, something potentially applicable to all social sciences. GIS, geolibraries, all of them relevant to all of the social sciences. It will occur to you, I'm sure, as I talk along these lines, that what you can say about the social sciences, you can also say about the environmental sciences. So don't think of this as strictly limited to the social sciences. You can use space to integrate across the environmental sciences just as much as the social sciences. So overall then, a more spatially oriented vision in future social science research. And we produced analyses at that time showing a ramping up of spatial concerns in social science literature. It really did seem circa 2000 that the social sciences were discovering spatial technology and spatial perspectives and spatial ways of thinking about problems. We had 6 programs, and so if we're going to talk later about specific programs that might further convergence, here are potentially some ideas. These are now, of course, 20 years old. This is 1999, but nevertheless, it's, I think, still relevant. So a program of workshops for graduate students and senior and junior faculty offered at selected locations around the nation. So we organized a series of workshops. Ohio State had a big role to play. Several other universities helped organize spatial workshops. A virtual community supported by internet-based interaction tools. And you'll find still a lot of material in GIScience.org, which dates from that period. A portal to learning resources in spatially integrated social science. We developed a lot of useful resources on specific topics in a spatial perspective. And a series of best practice examples, and those ended up in the book. So the book is essentially a series of best practice examples of how to use a spatial perspective across disciplines in the social sciences. And creation of a set of readily accessible and easy-to-use tools for analysis and exploration of spatial data. This was a point in history when geographically weighted regression was just becoming popular. And we ran workshops on GWR as a quintessentially spatial approach to analysis. And improved capabilities for organizing and finding social science information based on geographic location, the idea of a geolibrary or geoportal, which was very important at that time. Right. So there, from 20 years ago, is a previous attempt to achieve convergence based on space and, of course, time across the social sciences. I'd like to step back a little bit further and talk about what we term nomothetic science. And this is science as we typically know it from advances in physics or chemistry. It's scientific principles that are true everywhere at all times. And so examples would be the periodic table. It's true everywhere at all times. There's no question that the periodic table doesn't apply just as much on Tuesdays as on Wednesdays. Doesn't apply just as much in Arkansas as it does in the state of Washington. Right? Newton's laws of motion, again, nomothetic science. But nomothetic science is necessarily abstracted from space and time. There is no context. You can think of science, if you like, as a way of removing space and time from discoveries. Right? Because to be important in science, those discoveries must be true everywhere in space and time. So where does that leave space and time? That raises a very interesting fundamental question. And essentially the answer is this, that practical applications always have context, always exist in space and time. So to implement nomothetic knowledge, there must be space and time. Space and time are the key to knowledge integration. Not just knowledge integration, but also knowledge use. So here's a fundamental argument for space and time in convergence. You can't converge. You can't really have a serious conversation between a sociologist and an economist without involving space and time. Try to think of any other basis on which you can have a conversation between disciplines. And there's a real challenge for this meeting, I think. Is there any basis other than space and time for integrating knowledge? I'd like to go just one step further, and then I'll move on to some examples, and that's to talk about Occam's razor. So Occam's razor, I'm sure you encountered in fundamental courses in philosophy and philosophy of science particularly, and essentially it says simplification is a goal of science. There are various ways of expressing Occam's razor. I particularly like one I always believed was attributable to Bertrand Russell, which is, it is idle to do with many what can be done with a few. And I like it very much because it uses the word idle, which is very fascinating. But here's Thomas Aquinas's version. If a thing can be done adequately by means of one, it is superfluous to do it by means of several. For we observe that nature does not employ two instruments where one suffices. So this is the argument for simplicity. Given two explanations, two hypotheses, the simpler one is preferred necessarily. And of course we have some beautiful examples. One I particularly like is the Bohr atom, which simply explains the periodic table by saying that every row is adding a new electron and proton to a single layer of electrons. And similarly, each column has the same basic outer shell, outer layer in the periodic table. A very beautiful way of organizing 92 elements. Right? So let's come back to space then and think a little bit about how space might apply in this context. And one of the things that struck me in my first encounter with geography back in the 60s was the simplicity of pattern and the role of pattern in explaining things. And here's a lovely picture of patterned ground, which you can imagine that ground has been divided up into something approaching regular polygons. This sort of process occurs typically in periglacial environments. You find it quite commonly in the Arctic and in high altitudes. River meanders. It was a beautifully simple pattern and something that required explanation. And here's one that's a little bit closer to my own work. This is Rillenkarren, a process of erosion on limestone, which you find in karst areas, and I'm sure there's some examples somewhere in Arkansas of Rillenkarren. All right, but a beautifully regular pattern of channels, furrows, that are dissolved into the limestone. So one of the things that I've always enjoyed is, in fact, what ended up being my PhD dissertation topic, which are these things. This is on a cave wall. It's a wall in a cave in Watertown, New York, and it's Ordovician limestone. And those little scoops, if you like, they're called scallops. The scallops are, in this case, about 2 or 3 inches across, say 3 or 4 centimeters across. And in areas like in the Flint Ridge Mammoth Cave complex in Kentucky, these things can be 6 feet across. Right? And they always show the direction of water flow because they are steeper on the upstream side. So the water in this case was flowing from right to left. And they result from imperfections in the limestone, which causes separation of the boundary layer, a creation of an eddy behind the separation, right? And that eddy dissolves faster because the water is being mixed better, right? And so the eddy digs in, and so you get this pattern that eventually covers the wall. And essentially what you can do is this. If you take the density of the fluid, in this case water, the velocity of the fluid, and the viscosity of the fluid, and the length of these things, 2 or 3 inches, then you have a dimensionless constant and the numerical value is about 25,000. Right? So we can explain those things in terms of the rapidity of the water flow when this cave passage was flooded and when water dissolved the cave passage. Now, the beauty of this and the integrating aspect, the convergence aspect, is to go now to a snowfield in a high alpine area. And notice that it is covered with little pits. And these pits are similarly asymmetrical. And their size, if you take their length and you take the velocity, in this case of air, and the viscosity of air, and the density of air, you end up with the same constant. So it's the same process. In this case, though, it's not a chemical mixing, it's a thermal mixing of warm air flowing over a cold surface. And if you go to astronomy and meteorites, you find they're covered in little pits. And if you take the pit size and the velocity of the meteorite and the density of air and the viscosity of air, again, it's the same constant. So the same process applies perfectly across three very different domains. Okay? And here is the power then of pattern. The power of pattern to integrate processes across different domains. I always enjoyed this example as a particularly striking example. Right. Coming a bit closer to home, and a couple more examples. In GIScience, we have rasters and vectors, but why are there two possibilities? Are there any more? And can they both be derived from the same basic concept? Here again, simplification, integrating knowledge across different domains. And in this case, there's a paper that Mei Wan and Tom Cover and I wrote published in 2007, which argues that all of them go back to a single concept, which is what we call a geoatom. A geoatom is a tuple which says that at x in spacetime, some location in spacetime, the property z has a value of z of x. Right? And that's where all of our GIS data originate. They all originate from this concept that at some point there is some value of a variable. And that's it. And from that you can derive fields and discrete objects and vectors and rasters. They all essentially originate there. One of the most striking examples I came across at Santa Barbara years ago was from a professor in biology and brain science called Ben Rees, and his field of study is the retina of primates. Right? So all primates on their retina have two types of cells. And in the mature primate, the cells are distributed in a very regular pattern. The rods are regularly spaced among the cones. And his question was, what process can produce that? What kind of process can produce a regular spacing? And you might ask, similarly, what kind of process produces the spots on a Dalmatian or the spots on a leopard? Right? And so he looked around in different disciplines, and he discovered geography, and he discovered point pattern analysis in geography and the techniques of point pattern analysis that people have been using for centuries. Not to apply to the human retina, but to apply to human settlements over a landscape and other similar kinds of questions. Right? So rods and cones in the human retina perhaps are subject to the same kind of process, evolved using the same process that settlements did in the landscape of the state of Iowa, perhaps. And just one last example, and this one comes from, I don't know the original attribution of this. I know that it was work at the University of Washington in geography in the late 1960s, but by who I don't know, and where it was published I don't know. But here are natural levees. Right? Here's a river, and every now and then the river floods, spills its banks, and deposits. And so it develops natural levees. And those natural levees build up until some point where a flood breaks through them and invades the land around, and eventually the river diverts and finds a new course. And the argument they were making, this was a period when people were making these kinds of arguments about patterns, is illustrated here. Here is old US 99, which has now been downgraded as State Route 99, and essentially was the major route north from Seattle until massive development of retail activity along it made it essentially, slowed it down, made it hopelessly congested, whereupon a new route was developed, which is Interstate 5. Right? So think of these as natural levees developing around US 99, being broken through and eventually creating a new path for the river. Right? So we're drawing an analogy there, and we're converging between social science and natural science in this case. Right. So there are some examples, and I hope what I've got across is this notion that we need to think broadly, we need to think outside our own field in order to achieve convergence. So opportunities for the future, and where might we be headed? What are the potential areas of development for GIScience in the next few years? And if we take convergence as a theme, convergence in GIScience, and look for new directions, we can ask, where are those new directions, or what areas have long been under-addressed? If we look back at the history of GIS over 50 years, what areas has it tended to emphasize, and what areas has it tended not to emphasize? And it's easy to find examples such as we tend to have taken a two-dimensional approach rather than a three-dimensional approach, originating perhaps in the fact that maps were so important in the original development of GIS. Right? Maps are flat, maps form layers, and so inevitably we started to think in terms of 2D rather than 3D. And time. We tend to have emphasized things that are static because maps were made of things that were static. When maps were very expensive to make, it was much cheaper to make, well, much more effective to make maps of things that were static, because those maps would still be true in the future for a number of years. You wanted to maximize the length of validity of your map, you emphasize the static things on the Earth's surface. So time got shortchanged. But the one thing that has really long been under-addressed, to my mind, is mobility, flows, interactions, movements. Because these are difficult to deal with cartographically. And yet, of course, these days, we produce massive amounts of data on mobility and flows and interactions and movements. And we produce apps which allow us to visualize them very effectively. So I'd like to just play with that notion for a while, the argument that we have underutilized, underemphasized mobility, flows, interactions, movements in GIS and in GIScience. So let's go back to a classic, the Menard map, made in the 1850s and illustrating Napoleon's Moscow campaign of 1812, the Russian campaign. Right? So the French army left Poland, marched towards Moscow, and then backtracked all the way back to the Polish border. And this, of course, inspired War and Peace, and it inspired the 1812 overture. And the beauty of this, which is very much celebrated by Ed Tufte in some of his books, is that it illustrates not only the path, the route of the armies, but also the size of the army. Napoleon started with 660,000 men at the Polish border, and when he got back to Poland, was left with 10,000. And what I find absolutely remarkable is that Napoleon then went back to France and raised another army. I just wrote off 650,000 of your fellow Frenchmen. Come join my army. It also shows the major events, and it shows temperature. And of course, it was the temperature that was the main catastrophic factor in destroying the army. A beautiful map, a map of movement. And if we look for others, here's one that one of my PhD students put together. It's a very nice map of central Kentucky and Mammoth Cave is in here. And the blues are the known surface streams, and then the reds are the inferred flows underground. And in some cases, you can observe the stream underground, as in here and here and here, but in other cases, it has to be inferred, typically by dye tracing. Right? So mapping movement, showing maps of movement. If we run this forward to today, this is the kind of thing we have access to. Right? This is all pickups by cabs in New York City over a period, I think this is, what is it, about 6 months in 2015. Now we have access to this kind of data, and we are hugely rich in our access, the access now to mobility data. So this is stimulating asking research questions, and all sorts of literature is starting to appear. And here are just a few of the research questions that people have been addressing with these kinds of data. What do movements imply about the structure of the city? Which parts of the city perform which functions at which times of day? Can we identify functional regions, regions of the city, where one type of function is emphasized at some point in time? And regions of maximum internal travel. Which areas of the city are effectively isolated because travel is internal to that rather than across regions? Can we design better transportation systems? Because this kind of data is far better than what we've traditionally had. Right? Transportation systems in the past have been designed based on origin-destination matrices, the number of people who moved from one area to another area, divide the city up into traffic analysis zones or TAZs, and obtain data on gross flows. But we don't know which path they followed. We don't know what mode of transit they used. And we have then new information today on precisely those issues. Which mode of transport was used? What precise path did they follow? We know these things these days. And more research questions. Support for vehicle sharing. This kind of data is very useful to companies like Uber and Lyft, shared cars and cabs, dockless bikes, dockless scooters, all both collecting and utilizing this kind of data. We have some very interesting patterns emerging in Seattle. Dockless bikes tend to gravitate towards the bottom of hills. Right? It's hard to find a dockless bike at the top of a hill. So the owners of dockless bikes have instituted a process of discounts. If you leave the dockless bike at the top of a hill, you get it cheaper. Can vehicles be sensors? Yes. So Waze is a primary source for traffic congestion data. People are writing now about fine resolution mapping of air pollution. If you equip a few cabs with air pollution sensors, can you map air pollution in detail in space and time? And the answer, of course, is yes. And what is surprising is how few vehicles you actually need to equip, because taxi cabs, for example, tour cities very effectively. So how many sensor-equipped vehicles do you need to capture an adequate coverage in space-time? And so that leads me to the central topic of navigation. And I want to explore this a little bit because I've been doing some work in it, and I think it's a very interesting topic. So how do we find our way from A to B? And so given an origin and destination, find a route. And I want to think about that independently of the mode of transport. So this might be car, might be truck, it might be bicycle, it might be walking. And all of this depends on some objective function C. So what we need to do is, in order to explain a path, to find an objective function C that has been minimized or maximized by the choice. So C is the integral over the path of some measure of time, cost, friction, effort at S, a location on the path. And notice that S may depend on the direction of travel. So if you're at some point, it makes a difference if you're going uphill, downhill, or across the hill. No, unfortunately, that integral can only be solved for a very few very simple cases. So if f is constant, the path is a straight line, no problem. If f is a plane, the path is a simple curve which stays low, trying to avoid high friction, and then rises towards the destination. And that's solvable analytically, right? But other than that, we have somehow to discretize. And so various ways of discretizing, and this, from a GIS perspective, is very appealing, that we can reduce space to a mosaic of irregular areas. Each has a constant and isotropic cost, or friction, or F value. And at this point, there's a beautiful analogy to light. So, wow, we've integrated transportation and physics. We've converged two disciplines. Because light minimizes time. And it does so according to Snell's law of refraction. So when you come to a boundary between two of these irregular areas, there is an angle of incidence and an angle of refraction, and the ratio of the signs is a constant. However, and this is a big however, when you think about this, light also behaves according to the process of diffraction. There will be points of singularity in this map where light scatters. And because it scatters, you have an infinitely expanding search, unfortunately. And so this one essentially goes to a dead end. Or you reduce space to a raster. And you represent the path as a set of moves through the raster. And thinking of the analogy to chess, you can use the rook's case or the queen's case, and the integral becomes a sum. Right? So you either use 8 move directions or 4 move directions, or people have also experimented with 16 and so on. So here's a solution using this kind of approach, and every GIS can do this. It's trying to find the minimum cost path between 2 points where the cost in this case is represented by color. What I'm trying to do here is find a route from Santa Barbara, this is over the Santa Ynez Mountains, into a destination at the other side. And I've done it twice to illustrate the importance of the raster cell size. Right? So this one is with a 300-meter cell, and this one is with a 50-meter cell. And obviously, you can see the 50-meter cell is longer, apart from anything else. And both paths have tried to avoid the high ground by going through this relatively low pass. In fact, the highway 154 goes through this pass. This stuff has turned out to be quite appealing to archaeologists who are interested in why it was that native populations chose particular paths and developed trails. What were they looking for? What were they trying to minimize? And it's quite effective. In GIS, what I've done here is to illustrate this in terms of Orange County, California. The Pacific is down here, so Pacific is flat. And we're starting from a point at around where Santa Ana Airport is, John Wayne. And seeing how far you can get in different directions using a friction function, which is a function of elevation. So we're trying to avoid these mountains, which are on the northeast side of Orange County. And you can see that you get a lot further if you go through this pass, which is where California Route 91, I think, goes, up into the Inland Empire to Redlands and San Bernardino and Riverside. An interesting oddity here is that you would think, if I present the problem to you as, tell me how far you can get in a given period of time, you would think the answer would be circles. And if you naively approach GIS from that perspective, you would say, why haven't I got circles? Why have I got octagons instead? And I would then have to explain to you, this is because we solved this on a raster and we used 8 move directions. So you can actually get a little bit further in the same amount of time by going north or northwest than you can by going somewhere in between north and northwest. because then you have to combine, you have to make a jagged path. Right? But this is standard, and it's now widely used. But of course, in practice, if we're interested in transportation, we have to solve on a linear network, because a path must be a combination of network edges. And so we have an origin and destination on the network, and the network must be navigable, which means it must know about turn restrictions and overpasses and underpasses. But this is the field of guidance. It's what's in your guidance apps, and it's become very popular and something people use every day. What objective functions? We can minimize distance, we can minimize time, we can minimize energy consumption, we can maximize scenery if you like, we can minimize pollution, we can minimize danger. All of these are possibilities, and you will find them in different apps around the world these days. And here's a little example. This is my house in Santa Barbara. It's Seattle. And I'm trying to go for the evening to a concert at McCaw Hall down here near downtown. And I've asked Google for my route. And welcome to Seattle. Much of my route is red. And Google is recommending that I go follow I-5 down to here for a total of 23 minutes to cover 5 miles. Notice a couple of things about this. First, that it is not either the shortest or the fastest route, right, that's been recommended. What is Google trying to maximize? I don't know. I can try and reverse engineer it, but Google is not public about what they're trying to maximize or minimize. And notice also that the two alternative routes are significantly different from the recommended route. Because intuition would say that the second best route is a minor deviation from the first best. To have a major deviation, I have to be doing something a bit extra. And this is, in fact, a version of this problem that a colleague at Santa Barbara, Rick Church, has published on extensively, where you're trying to find routes that are not quite so bad, but significantly different from the best route. And it's not simply a matter of finding the second best route and the third best route. I think this is totally amazing that we can get that in less than a second for any pair of locations. That underlying that is a point of interest database, which is, for the city of Seattle, at least 10 million entries. And every street, every laneway, every sidewalk, everything is in there. It's just amazing that we've come to this point with this technology. Here's one of the questions that people often ask. If you were to recommend an alternative, if you had some congestion and were to recommend an alternative and a lot of people were using the same guidance app, then wouldn't they create a worse problem? And yes, here's a simulation with 20% of drivers using mapping apps where following a diversion has created a worse congestion than the congestion they were trying to avoid. That sort of thing is the kind of question that I think people often have. In terms of alternative routes, alternative modes of transport, we can do transit, right? These days we can do walking. Google will combine transit and walking. Or you can do bike, but there's no combination of bike and walking or no combination of bike and transit. But here's an example of, this is me in Hong Kong, trying to go from my hotel to a point on a bus stop where I'm going to take a hike. And it's combining walking and rail and bus. And one thing that this does not do well, you can see it tells me to walk from my hotel to Hung Hom Station, but it doesn't tell me how and what route to follow and which entry. There's at least 15 entrances to Hung Hom Station. And when I need to transfer here onto a bus, it doesn't tell me that when I get off the train, there are at least 100 bus routes that converge on that point. It doesn't tell me how to get to the one that I need. So we are a long way from perfection in this kind of technology is my point. There's one very nice piece of work. My colleague Waldo Tobler at Santa Barbara, who unfortunately passed away a couple of years ago, developed what he called the hiking function. And this assumes an average human and looks at the speed of the human as a function of slope. And this is directional slope, so it takes account of whether you're going upslope or downslope. And there's a lovely quotation from the paper. There's the reference to the paper. I find this particularly exciting and have worked out a simple example for walking in variable terrain using the hiking function estimated from empirical data given by Imhoff. A classic quotation from Waldo Tobler, who was very much an aesthetic scientist. Here's his function. So it's a negative exponential, and slope is the tangent of slope angle, and it's signed. And direction of travel and speed is in kilometers per hour. So this maximizes at 6 kilometers per hour for a slight downslope. It's a downslope of about 2.9 degrees. So the idea is you maximize your walking speed when you're walking slightly downhill. And so this is one thing I like about this area of research is that you can test it on yourself. So you can go out and collect data. This is some data published by Keith Clark, and it shows, here's the hiking function, this reddish line, and here's some empirical data from West Point students. And we assume these West Point students are average humans. They do find some difference between men and women, but not very much. And notice that the downspeed is quite underestimated in practice. That's something I'll come to in a moment because it raises some questions. Here is some work by Chris Higgins in Hong Kong working on himself. So he keeps track of himself using Strava and plots the results. And again, you can see that the peak is somewhat underestimated. And here's me. I found a nice piece of road in Hong Kong, 1.6 kilometers long, with a pretty consistent slope of 0.088. And I was quite a bit faster than the Tobler hiking function going uphill, and a little bit slower going downhill. But notice the technical issues, and here's a strong link to GIS. If you want to do this kind of thing, there are some technical issues, right? Number one, what's your source of slope data? Right? Because if you're using GPS, GPS has notoriously poor vertical accuracy. If you're using a digital elevation model, you are almost certainly underestimating slope depending on spatial resolution. The instantaneous slope, which is what affects the hiker, is not the same as slope measured from a DEM. Right? And we can say something similar about the source of speed data. If you're using GPS, you've almost certainly underestimated the distance traveled because of the sampling interval of the GPS. If you're using map matching, you're matching to a polyline representation, which again almost certainly underestimates distance. Here's a much more general version of that whenever length is estimated from a GPS, from a GIS, it's almost always an underestimate. So we can go beyond the average human because we can ask about gender, we can ask about age, what happens as people age, what happens about people with walkers or wheelchairs. All of these important questions to the concept of aging in place. And fitness, and load carrying. What is the hiking function for a backpacker? So a number of key questions arise, and I think the central question is this: how can advanced hiking functions, and I put hiking in quotes because I'm talking about multiple modes, there's no reason why this shouldn't apply to cars or trucks. How does it affect our current generation of navigational aids? Our ability to design cities for greater mobility, less dependence on traditional modes of transport, aging in place. And now I'd like just to go one step further, because I think this is the beginnings of something much larger in terms of the opportunity for mobility research. And so let's now go to this hike that I was planning to take in Hong Kong from this bus stop. It's about, 3 hours of hiking to Sai Wan Pavilion, where I'll get a taxi. And what I've done here is to access a central store of data, in this case, Google's data on navigation. And as I hike, I'm combining that with my own senses. So here's a point on that hike. This, believe it or not, is Hong Kong, which you always thought about as a massively overpopulated city. And what I'm doing here essentially is modeling what happens with a field robot. So field robotics is the study of unmanned vehicles, aircraft, agricultural machinery, which are behaving as robots. And central to that is a combination of locally sensed information and centrally stored data. Right? As a human, I have senses, but I also rely on centrally stored data in my apps. As a driverless vehicle, I similarly rely on a combination of what is sensed and what comes from a central store. And the technical term for this is SLAM, simultaneous location and mapping. The robot must be capable of locating itself and also mapping its surroundings. It can locate itself by relying on a central store, but also mapping its surroundings. And both of these, of course, are geospatial operations. In fact, the whole thing is geospatial. Yeah? So schematically, you might think like this. You have a central store with network data, point of interest data, and a routing algorithm. You have a field robot with its own sensors, and the combination of the two produces an autonomous vehicle. Then there's also a flowback, because the data being sensed by the robot can also enhance and correct the central store. The user, as a human, may volunteer updates and corrections to the central store, but a field robot may also use its sensors to augment, update, and correct. Right? So there are some very important questions here. What kind of spatial resolution is needed? What kind of positional accuracy is needed by the central store? And right now there are companies all over the world who are extending existing databases to the decimeter and centimeter level. If you have an autonomous vehicle that needs to know which lane it's in, then the central store needs to have decimeter level accuracy. And if it needs to pull up at a gas pump or park in a parking space, again, it needs decimeter level accuracy. But at the same time, the sensors on the vehicle are operating at centimeter and decimeter level. So what is the appropriate division of responsibility between the two? I know what it is for me as a human, but I don't know what it is for a driverless vehicle. And just to finish, here's what I find to be an interesting speculation. Alan Turing and the Turing test. The Turing test asks, if you have something behind a wall and you ask it a question, how can you tell if what is behind the wall is a human or a computer? The Turing test is passed if what is behind the wall, if you can't tell whether it's a human or a machine. Right? So how does that apply to vehicles? Right? What is an appropriate Turing test for a vehicle? How can you tell whether it's being driven by a computer or being driven by a human? And so central question here then is, what might such a driver know that is not currently provided by informatics? What do expert drivers, such as cab drivers or delivery drivers or habitual commuters, know which these systems are not currently aware of? And there are many examples, right? So synchronized traffic lights. I don't know of any any wayfinding app which knows about synchronized traffic lights or anticipated future congestion and many, many other similar questions. So will we at some point reach the ideal situation where you cannot tell whether a vehicle is being driven by a human or a machine? Interesting question. So just to reiterate some of the key points, convergence has long been a theme of GIScience across both the social and environmental sciences. What does this new initiative by NSF mean for a field that has long been concerned with convergence? Similarity of pattern can imply similarity of process, but there's an important caveat here, the principle of equifinality, that the same pattern can be produced by more than one process. And then finally, I believe that research on mobility is one potentially very rich direction, future direction for GIScience. So thank you very much for your attention.